talked about momentum, and let's just kind of review the equations that we know so far. Momentum is a vector, and it is the moving inertia of something. So it takes into account the mass and the velocity of it. So when you plug in for V, mv, V is going to have positives or negatives or directions associated with them. And whatever the direction the object is moving in is the direction of its momentum. In order to change your momentum, you have to apply an impulse. And in fact, the impulse is equal to that change in momentum. And it is equal to the force times the time over which that force is delivered. And by definition, force is not the change of momentum, but the rate at which momentum changes. If the momentum changes in a smaller amount of time, then more force is required. And if the momentum changes over a larger period of time, less force is required, which is why gymnasts use mats. It's why you use a glove. It's why we have seat belts, and those are effective because they extend the amount of time over which the momentum changes on your body, which decreases the amount of force on you. Now let's talk about our next conservation law, the law of conservation momentum. And this is really important because when we talked about Newton's laws, we said, okay, he defined what moving inertia was, he defined what impulse was, and he defined what those were in the first law. And then he talked about this force, push or pull, that changes the momentum of something. That was the second law. And then he said that these forces always come in pairs. So that is tied to this idea of the law of conservation of momentum. All right, so we all know that if we fire a gun, it's going to recoil. And that's because we've learned in the past that there's a force on the bullet, and there's always an equal and opposite reaction on the gun. But the real reason it happens is because of conservation momentum. The total momentum of a system stays the same unless an outside force acts on it. So what is the total momentum of a system? Well, let's talk about this gun. The momentum of the gun plus the bullet to start with has always got to stay the same. So after it's fired, it has the same total momentum. So let's talk about that. Well, to begin with, the bullet is sitting inside the chamber here. Both the gun and the bullet are at rest. So the bullet of the gun plus the bullet momentum of the gun, both of these are zero. So there is zero total momentum. So afterward, all of a sudden, the bullet is moving, which means that, let's kind of do this up here where we have more room. So 0 equals whatever the momentum of the gun is plus whatever the momentum of the bullet is. So if I rearrange this, the momentum of the bullet is going to be equal to the negative momentum of the gun. Which means that the gun has to recoil with a velocity in the backwards direction so that, excuse me, so that it has a momentum in the negative direction that cancels out the forward momentum of the bullet. And this is why there is always an equal and opposite reaction. This is why the third law exists. It would not exist if momentum wasn't conserved, and especially if momentum wasn't a vector. If it didn't matter what direction an object was going, momentum didn't have that factor in it, we wouldn't know which way the bullet would go. I mean, we wouldn't know which way the gun would go. It could go forward or backwards. So consider a bug hitting a windshield. So here's windshield, here's the bug. The force on the bug is equal and opposite to the force of the car on the bug. So if the bug hits the car is going to hit it equal and opposite. And the amount of time that it happens for is going to be the same. So the impulse is equal. But, and they both have the same, that doesn't make sense at all. Sorry. My bad. Totally taking this too far. Don't listen to that. The force of the bug and the force of the car are equal and opposite. But which one's going to have the bigger change in momentum? Well, the bigger change in momentum is going to be the bug, right? Why? Because it's actually going to stop, right? And why? Not because it has more force on it, because its body can't handle the force that it does have on it. It just doesn't have the material, internal strength to be able to handle that force, and so it goes flat. So the bug has a greater change in momentum than the car, right? And that makes sense, right? Change in momentum means a change in velocity. Which one slows down the most? The bug does. It may even stick to it and move around and bounce, right? All right, let's do an example. A 70-kilogram hockey player catches a 1-kilogram hockey puck. So what this means is that the total momentum before has to be equal to the total momentum after. And what are the two objects? We have a player and we have a puck. So we have the momentum of the player and we have the momentum of the puck. So a 70-kilogram player catches a 1-kilogram puck traveling at 15 meters per second. So afterwards, he's, before the puck is flying at him and he's right here, right? And afterwards, he now has the puck in his hand. So afterwards, it's going to be the momentum of the player plus the puck. So the momentum of the player, we're going to assume, is 0 to begin with, but the puck is traveling at 1 kilogram times 15 meters per second. Afterwards, they're together, so their total mass is 71 kilograms times whatever their speed is. The speed is going to be 15 divided by 71, or 0.211 meters per second. And it's positive they're moving in the same direction as the puck was moving. Pretty easy. All right, let's look at a collision problem. A 2,000-kilogram car is traveling at 2 meters per second. So here's our car traveling at 20 meters per second, and it's going to hit a stationary car. And afterwards, we'll call this A and B. And afterwards, it's going to bounce back and we don't know what car B is going to do. Let's figure it out. So the sum of the momentums before is equal to the sum of momentums after. We had a 2,000-kilogram car traveling at 20 meters per second plus a stationary car, 0, is equal to the 2,000-kilogram car traveling at negative 10 meters per second. Negative, right? It's in the opposite direction. Plus stationary car of the same mass, so it's 2,000 kilograms times its velocity, So this is going to be 40,000 units of momentum equals 20,000 in the negative direction plus 2,000 kilograms times V. So I'm going to have to add 20,000 to both sides. So that becomes 60,000 kilograms meters per second equals 2,000 kilograms times velocity. The velocity is going to be 60,000 kilograms meters per second divided by 2,000 kilograms, or 30 meters per second. So this car is going to be moving to the right at 30 meters per second. I know that because this is a positive value. So it's going to be moving like that. So when you add these together, the momentum of A and momentum of B, it ends up to be the same momentum that they had to start with. Two skaters, one's 50 kilograms and the other's 80 kilograms, push off of each other. So we've got skater A and skater B. So before, they're just standing there. They all have a velocity of 0. And afterwards, the 50 kilogram goes backwards. So the smaller one goes backwards. And we want to know what happens to B. So the total momentum before equals the total momentum after. Notice how I'm doing this every single time. I'm writing my general equation. Then I'm looking what's going on. Before, the total momentum is 0. And afterwards, it's the 50 kilogram times negative 20 meters per second, because it's going backwards, plus 80 kilograms times velocity. So 0 equals 100 kilograms meters per second, and it's negative, plus 80 times V. Then we're going to add 100 to both sides, so 100 kilograms, actually it's 1,000, sorry, 1,000 kilograms meters per second added to both sides equals 80 kilograms times V, and V equals 1,000 kilograms meters per second all over 80 kilograms. And when I do that, I get and this was positive, so I'm going to get 12.5 meters per second. So it's going to be moving to the right at 12.5 meters per second. It's because it's positive. So what are elastic and inelastic collisions? So an elastic collision is where momentum and KE are conserved. So an example of that would be if you had like a 1 kilogram ball traveling at 10 meters per second that hits a stationary 1 kilogram ball. And afterwards, the first 1 kilogram ball is stationary and the next 1 kilogram ball is now moving at 10 meters per second. Here's an example. So how would we do that? Well, let's just verify that the P before equals the P after, right? It does, because it would be 1 kilogram times 10 meters per second plus 0 equals 0 plus 1 kilogram times 10 meters per second. So you can tell yes, that is true. And it's always going to be true. The momentum before and after is always going to be the same. But what about the kinetic energy? So if we add up all the kinetic energies before and we look at them after, are they equal? Well, the first one has 0, and the second ball is 1/2 of 1 kilogram times 10 squared equals question mark. Oops, I'm sorry, it's the other way around. Plus 0. Sorry, looking at the wrong side. Equals 0 plus 1/2 of 1 times 10 squared. If I do that, that will be 0.5 times 100, or 50 joules, equals 50 joules. So yes, this is an elastic collision. What about an inelastic collision? So let's take the example of the boy and the girl. Or let's take the example of the train. So we had a 2,000 kilogram train, and it was moving at 20 meters per second, and it hit one that was at rest, and afterwards they stuck together. First of all, let's figure out what they do, right? So if they stick together and they keep moving, in order for momentum before to equal momentum after, the 2,000 kilogram times 20 meters per second plus 0 has to be equal to 4,000 kilograms times V. If we do our math, V is going to be equal to 10 meters per second. So we know that these are going to move off at 10 meters per second. But what's happening with the kinetic energy? Well, the K before, is it equal to the K after? Well, before, the only thing that had kinetic energy was the first car, 1/2 of 2,000 kilograms times 20 meters per second squared. And we want to know if that's equal to 1/2 of 4,000 kilograms times 10 meters per second squared. So if I do my math here, this is going to be 1,000 times 400. So 400,000 joules. And we want to know if that's equal on the other side. Is this going to be 2,000 times 100, or 200,000 joules? No, it's inelastic. The momentum is conserved, of course, always, 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 but the kinetic energy isn't. So the change in kinetic energy was you went from K final minus K initial to 100,000 joules minus 400,000 joules. So you lost 200,000 joules of energy. What did it turn into? Heat, because of friction. So there was 200,000 joules of heat generated during the collision. That's conservation of momentum.